And this is like 30 minutes after we got out of the cave. 3.6?
No, 6.
6,000 counts per minute?
Yes.
On my body?
Yes.
Oh gosh, that's crazy.
Giant Leap with Taylor Wilson.
Taylor, you showed me and our producer Phil Corbett this video of you leaving Carlsbad Caverns in New Mexico, and you're breathing onto your Geiger counter in the car, and it's going off.
Going crazy.
I really hate that.
It's a little disconcerting.
You're breathing in something radioactive and then breathing it back out, continuously?
Yeah. Well, I mean, as you know, I carry a Geiger counter on all my vacations.
I do know this.
Which in this case was a good thing because Carlsbad Caverns, famous national park, beautiful cave system, by the way. If everyone hasn't visited, they should go visit. But as with a lot of cave systems, because they're underground, they trap naturally occurring radon.
Okay, didn't know that. That's everyone, obviously.
Yeah. But you know about radon, right? Like, probably had your house tested, maybe.
Yeah, that's what I was gonna say. Like, there's radon detectors, the way that we have like smoke detectors.
Yeah, because radon is an odorless, colorless, radioactive, naturally occurring gas. It comes from the decay of the primordial radioactive elements like uranium in Earth's crust.
What formed Earth, yeah.
And take uranium, for example, as it decays, into lighter and lighter isotopes. You go down, you get radium, and then radium decays into radon. And radon decays into these solid daughter products is what we call them. They're just the products of the decay of the radon.
So you kind of have the isotope, which is
a parent and a daughter.
And that's like the thing that's coming off of it.
Yeah, we call it a decay chain, right? So one element decaying into another element, decaying to another element or isotope. And towards the end of this decay chain of uranium, you have this gas radon. And what it decays into are these solid daughter products.
So radon is not an element on the periodic table.
It is.
It is.
It is, yeah.
Okay.
Yeah, it is the heaviest naturally occurring noble gas.
Noble gas, okay.
And
I thought noble gases were fine, right? Like xenons.
Chemically inert.
Okay, but we shouldn't be breathing them.
Not if they're radioactive.
Okay.
Like radon.
Okay, yeah.
So here's this naturally occurring radioactive gas. It's very heavy, so it tends to accumulate in things like basements, or in this case, the video I showed you, a cave, Carlsbad Caverns.
Don't love that.
And the radon decays into these solid daughter products, things like bismuth and lead that are radioactive.
I didn't know bismuth is radioactive.
Well, actually, all bismuth is slightly radioactive, but certain isotopes are more radioactive than others. And so anyway, you've got these daughter products. And so if you're in a place like Carlsbad Caverns that has a lot of radon and you breathe it in, well, that stuff is kind of inside of you. And that's what I was showing you, is breathing out onto this.
Are you concerned for your health?
Well, if I was there every day, maybe. If I had those levels in my basement or in my house, I would be concerned.
Yeah.
Occasionally being exposed to that, it's not going to be terrible, but it is something that, if that kind of level was in your house, you should be worried about.
Okay, yeah. What are it just causes cancer.
Yeah, exactly.
Okay.
It's irradiating your lungs, those daughter products. But what's so interesting is, so that's the decay chain of uranium. You start with these uranium and the rocks and the ground, and the radon comes out, and then you end up with eventually stable, lead is the kind of continuation or the bottom of that decay chain.
Also don't want to ingest that or breathe that in, but for other reasons.
Yeah, but the decays emit alpha particles, and alpha particles are fine when they're outside of you because they can't penetrate the skin, the dead skin layer. It can't hurt you if it's outside of the body.
Okay.
But if alpha particles or sources of alpha particles, what we call alpha emitters, get inside of you,
bad.
It's a really bad day.
If I had a cut and then it got
some of that into you, that wouldn't be good. So think about the canonical, the radium girls, the radium, the radium dial painters that licked the tips of the paintbrushes as they were putting on the luminescent dials of a clock.
I've never heard of this. I didn't know that.
Oh, you should definitely look
up
into
the
that.
radium girls. I guess I shouldn't be laughing.
No, there's amazing biographies and documentaries on the radium girls, but this was really important in the history of what we call health physics, or the study of the dangers or the health effects of radiation, because really, in a lot of ways, before the radium girls, if anything, we thought radiation was good for you. I mean,
right.
I've showed you examples.
You have all these things in here off camera,
yeah.
and that are a mug, and if you drink drink from it, you'll get all these benefits from radiation.
Yeah, so I think like I've showed you the Revigator, which is a water crock lined with uranium ore, and the idea was it says on there, drink like 5 times a day for optimal health. And I guess it kind of makes sense when we first discovered these radioactive elements. When Marie Curie first discovered radium, they gave off tremendous amounts of energy. So they're giving off a lot of energy. Take that inside of you, it must give you energy.
That's why I eat batteries every day.
Right. But you can see that kind of that logic,
sure.
Because we didn't know the negative health effects. And it wasn't until later on, maybe a decade later after the discovery, that we started to have examples, whether it was because of X-rays or internal or external exposure to these radioactive elements, that, oh God, that this is not something you want to mess with.
Okay. So I shouldn't be using the Revigator?
Probably not.
We'll lock it up.
Yeah. But I think that's a good example of, the radium girls being one of the first, examples of how radiation can be very, very harmful if these elements like radium are taken inside of you. They can be externally dangerous, but if they get inside of you, then they continually irradiate you from the inside out. And these poor young women that would lick the paintbrushes to paint the dials on the clocks ended up with these very large, we call them body burdens, of elements like radium.
And they're ingesting
the health effects were terrible. So, okay, where were we going with this? Well, these elements emit alpha particles, the decay.
Not scary outside.
Not scary outside the body, but very scary inside the body. Well, what is an alpha particle?
The first alpha, the first particle.
Well, alpha particles are unique. I mean, we talk about ionizing radiation. We talk about alpha, beta, gamma. You've probably heard about gamma rays, right?
Yeah, those are the bad ones.
Well, they're the penetrating ones.
Sure.
And gamma rays are just light. They're just photons. They just happen to have a very high energy.
Okay.
So unlike
if I'm like near like a nuclear site of some sort,
you might get exposed to that external gamma
That's
radiation.
what happened to like the people at Chernobyl.
Yeah, and the Hulk.
Oh, cool. Okay.
But I think that's a good example of it's high energy light. It's higher energy than like visible light or even ultraviolet, but it can penetrate and it can cause that harm from the outside. Same thing can sort of happen with beta particles too, and those are electrons. So the particles that are around atoms that carry
their high energy
electric charge. Those at high energy are what we call beta particles that originate from nuclear decay. And then alpha particles are even bigger. And what an alpha particle is a helium nuclei. So the same stuff you put in balloons, make them float away. If you strip the electrons, the negative charge off of those atoms, that is an alpha particle. So this leads to
there's a bunch of helium.
Yeah, this leads
around.
to an interesting
Literally
question.
Floating.
Well, in a lot of cases, yeah. I mean, that leads to an interesting question of like.
Okay, Taylor, there was a very loud noise outside of the studio. Everything's fine. We were talking about alpha particles and helium.
Yeah, so an alpha particle, two protons, 2 neutrons.
Okay.
It's a helium atom that's missing its electrons.
Okay.
And that kind of leads.
Did it have no electrons then?
Yeah, it's ionized. It's fully ionized.
Okay.
Yeah, so. Because where does it come from? It comes from a nucleus. So
it comes off of something else, doesn't have any electrons because it doesn't start with any electrons.
Exactly.
Okay.
So the best way for a really big atom that's unstable to become stable is to give off a lot of mass. So like some
helium.
things can give off beta particles, think like tritium or cesium-137.
I always think about that.
Whatever. Or if their nuclei is charged up, got a lot of energy, it can relax by emitting gamma rays. But if you're a big nucleus, so we're talking about radon, radium, radioactive lead, you name it, uranium.
It sounds like an insult. If you're a big nucleus.
Yeah, well, that's the thing. They need to be on a diet. They need to lose some weight. And in this case, to do that, they emit a lot of mass in the form of these 2 protons and 2 neutrons. That is a helium nuclei. And those nuclei are where all our helium comes from, because we really shouldn't have helium. It's a very light element.
Like all of the helium that we like fill our balloons with at some point came from like a nuclear reactor, like letting off.
Well, not a nuclear reactor,
or some sort of
but some sort natural radioactive decay of this uranium decay chain we were talking about.
So it only comes from uranium. It's not coming from other like plutonium.
Well, plutonium there's not a lot of that left, you know.
Okay.
But primarily thorium and uranium. Those
Okay.
two elements, their decay chains, have these alpha decays. And when they decay via alpha decay, they emit these alpha particles.
So if we find like a pocket of helium like underground, that's probably close to something radioactive or
well, I mean,
formally
surprisingly,
radioactive.
that stuff migrates a lot, which is how the radon ended up in Carlsbad Caverns.
Interesting.
It's interesting. It's actually adjacent to the Permian Basin, and the Permian Basin is a massive oil and gas field in southeastern New Mexico and West Texas. And the Permian Basin's this huge reservoir of oil and natural gas. It also has a lot of radon in it. So these oil and gas fields typically have a lot of helium in them. They also have a lot of radon, and that's because, one comes from the other. And when we talk about, gas and oil formations as being trapped geological formations, they typically have a cap. We puncture these capped geological formations, and we unintentionally suck out the radon, and we capture the helium and use that to fill up your, party balloons and
I heard there's like a
dirigibles.
helium shortage and that could be quite concerning.
Yeah, I mean, a lot of that just has to do with policy more than anything else. Like,
okay.
We have like sufficient geological reservoirs of helium. We don't always do a good job of a society of maintaining that and selling that and prioritizing it.
Yeah,
Things
like maybe
that.
our birthday balloons are not as important as some scientific uses for helium that I totally know.
Like MRIs.
Oh, okay, all right.
NMR magnets. Liquid helium cools down the superconducting magnets.
Okay.
Liquid helium is that's another episode, but that is a super cool, we've talked about superconductors. But
and you can like superposition, you can like put something.
Yeah, but talk about superfluidity. That's even more interesting in helium-3, which is a whole nother story. So everything we've been talking about is helium-4.
Helium gas.
The stuff in your party balloon is mostly helium-4. But there's another isotope of helium-3, an isotope of helium that doesn't come from radioactive decay, so there aren't these big natural reservoirs of it. That is a fascinating element. It could be used for nuclear fusion. It can be used for superfluidity and cryogenic low temperature physics research. And we don't have much of that. The only helium-3 we really have is from decommissioned nuclear weapons and tritium stockpiles, which is used to boost hydrogen bombs or thermonuclear weapons. And we get a little bit of helium-3 from the decay of tritium. But if we decide as a society, say we want helium-3 deuterium fusion power plants, we'd have to probably go to the moon. And there are all of these proposals to mine the moon for helium-3.
Oh, wow, okay.
Have you seen the movie Moon?
I have, yeah. It's a great movie.
Yeah, it's about helium-3 mining.
Oh, okay, that's their mining.
So that's where helium comes from.
Wow, I mean that's
decay.
That's great. I guess I had no idea. So bringing it back to that video that you talked about. So are you where's that helium coming from inside of you? Are you breathing out helium? Why isn't your voice higher pitched?
I guess I'm breathing out a small amount of helium.
Just so little.
So what am I breathing out? I'm breathing out radon from the cave, probably more specifically the daughter products of the radon. And every time they're alpha decaying,
a little bit of helium.
If they find a couple of electrons, they're becoming helium. So yes, I'm breathing out a few atoms of helium.
Okay.
But if you do that experiment on a very large scale over, millions of cubic feet and you trap it underground, eventually you're going to make a reservoir of helium. And then those are the reservoirs of helium that is where we get helium from.
All right, cool. Don't be concerned about going underground at Carlsbad.
Unless you smoke. The radon hazard is much worse if you smoke. Okay, so maybe just don't smoke.
Sure, don't smoke. You heard it here first.
There's a PSA.
Yeah, all right. Well, thank God for Giant Leap and telling people not to smoke. And
get your basements tested for radon.
Get your basements tested for radon. But yeah, if you go to Carlsbad Cavern, you're not gonna die. You'll be okay.
You're fine.
Yeah.
And more example of, naturally occurring radiation being all around us. I talk to people all the time. They're like, oh my gosh, radiation, it comes from atomic bombs and nuclear power plants. And it's just a reminder that, this stuff is all around us. It has been with us since the dawn of time.
Every time you fly, you're getting irradiated.
Yeah.
Every time you're doing anything, there's some amount of radiation around you.
And obviously, you should minimize your dose to radiation as what we call in health physics as low as reasonably achievable. But,
you'll never avoid it altogether.
You're never going to avoid it altogether.
Cool. All right. Well, thanks so much, Taylor.
That's one small step for man, one giant leap for mankind.
leads to an interesting question of like, what was that?
I don't know. We should probably go look that
I'm
up.
gonna go check real quick.
Yeah.
We'll just keep recording.
I'm gonna pause it.
Okay. Underground.
Yeah, so in the same way that we produce natural gas, we suck out the...
Cursed episode, Taylor. The recording stopped, but we're back again.
There's no helium 1 and 2 because... Well, there's no helium-1 because, anyway, let's cut that because that gets way too complicated. But helium has 2 protons, so if you you could never have a nuclear mass of 1 if you have 2 protons. Anyway, that's not important.
Yeah, where are we?
Where are we? Where were we going with that? Oh, we were talking about helium-3. So, okay, so